So this is another paper about TLS 1.3, and like Cedric said, this is the new beautiful version of TLS, which has been completely redesigned from scratch. And after 20 versions, it's pretty much ready for standardization now. So it's worth asking and remembering, why did we need a new protocol? Well, the first reason is security. The number of broken crypto constructions in TLS 1.2 and earlier versions had gotten so large that people decided they needed to completely redesign it from scratch. And if you don't remember what these broken constructions are, maybe you remember all the catchy attacks that came out of the last few years, almost all of which rely on breaking and exploiting legacy crypto in TLS. The second reason, like Cedric also said, was efficiency. To reduce the number of round trips you need to wait for before you can start exchanging data. So both secure and more efficient, and this seems like too good to be true, and of course, there are trade-offs between, but these are potentially contradictory goals. So the protocol needs extensive security analysis before deployment, and consequently, the IETF decided to ask the academic community at large to come and help them formally analyze the protocol before it is standardized. And there was a very good response to this. There have been proofs about the protocol in crypto proofs, symbolic proofs, and as we've seen, even a verified implementation of the record protocol. In our paper, we do a little bit of all three of these things. So we've got a bunch of proofs of the protocol. So are we done? Is it secure? Can we go home? Well, the key question here from a practical viewpoint, from a practitioner's viewpoint, is if today we took TLS 1.3 and we deployed it on servers that are already running TLS 1.2, then would it expose new attacks? Would it prevent previous attacks? How confident can we be? And this is a question which normally with so many proofs should be easy to answer. But in the context of TLS, the relationship between TLS and its proofs has had a checkered past, let's say. There have been various proofs of earlier versions of TLS which did not find attacks which were found many years later. And this is because proofs of TLS have typically relied on simplified models of the protocol, and the gap between these models and the deployed protocol was so large that attacks slipped through. For example, some early proofs ignored ugly implementation details like padding, and so they did not think about padding Oracle attacks. Other proofs, including those developed by me and my group, for example, would ignore composition between popular modes of the protocol and unpopular modes of the protocol, like renegotiation, and you would miss some attacks there. Sometimes the proofs would have crypto assumptions that were much stronger than those used in the protocol. For example, you'd assume that all the hash functions used in the protocol are collision resistant, while the deployed protocol would use MD5. So these gaps that you have between the models and the implementation led to a whole bunch of attacks. And so now before we certify TLS 1.3, it would be good to sort of ensure for ourselves that our brand new TLS 1.3 proofs are not falling prey to the same traps. To this end, we propose our approach, and we advocate the use of mechanized proofs and automated verification tools to handle the complexity of the whole protocol, and to enable, because we think these mechanized proofs are easier to maintain over time and add features to and re-verify the properties than a hand proof would be. We advocate the use of symbolic analysis to test the protocol against large classes of known attacks so that we can find attacks like downgrade attacks automatically. We want to build a mechanically checked cryptographic proof of the protocol, like, for example, the one that the TLS project is building, so that we can explore the various cryptographic assumptions that may or may not be needed for the security of the protocol. And finally, we want to synchronize our symbolic and computational models with the RFC itself and make sure that we are not too far from the standard. And to this end, what we advocate is using a reference implementation, which we have developed called RefTLS, and automatically extracting the core protocol functionality from it. So in an ideal world, this is what we would have. We would write one model in our setting. We'd write one model for TLS 1.3 and use it in three ways. We'd use it for symbolic analysis to find attacks, fix them, re-find attacks, and so on. Once we can't find any more attacks in the symbolic world, we would do a computational proof. And once we have done our computational proof, we would use the same model as part of a reference implementation. What we have right now is not as nice as this. What we have is a tool chain where we write three different artifacts, a symbolic model, a computational model, and a reference implementation. And we link them together using a combination of automated tools and manual edits and so on. So it's not as nice as the picture that we would like to be at when this process ends. So in the rest of this talk, what I'm going to do is sort of show you some snippets of what we can achieve with this tool chain. and for most of the details, I refer you to the paper. So the first example I'd like to look at is how you can use symbolic analysis to find downgrade attacks. So here's a list of the attacks that I flashed earlier on the slide 1. These are all fairly recent attacks on legacy crypto use in TLS. And when you look at this list, the first question many people ask is, why are TLS libraries still supporting such old and obsolete crypto mechanisms that we should have gotten rid of a long time ago? The answer for all of these things is always backwards compatibility. I mean, not just forget about this, right? If TLS 1.3 is deployed today, it's going to be deployed alongside TLS 1.2 because, of course, not everybody is going to be supporting TLS 1.3 on day 1. So you're going to have an implementation that does TLS 1.3 and 1.2 for backwards compatibility. But that raises a new question, right? So the good news is that TLS 1.3 doesn't have any weak crypto. The bad news is it's going to be running alongside TLS 1.2, which does have all this weak crypto. So how do we know that TLS 1.3 will still be secure if it is deployed alongside older versions of the protocol? In particular, we're worried about downgrade attacks. Can a man-in-the-middle attacker take a connection between two TLS 1.3 peers, who should really be talking 1.3, and downgrade them to use weak crypto or an old version or something like that? In order to find such attacks and to be assured that such attacks don't exist in TLS 1.3, the first thing we have to do is to model weak crypto, right? This is a bit unusual in symbolic analysis because symbolic analyses called $VIO models typically treat the cryptographic primitives as perfect black boxes. Instead, what we do is we model them as agile functions that take the algorithm as a parameter. If the algorithm is strong, then it behaves just like a perfect black box. If the algorithm is weak, then it's catastrophically broken. Okay? For example, if you want to model Diffie-Hellman key exchange, on the left-hand side is the classic ideal Diffie-Hellman kind of equation in Proverif. It says that g to the x to the y equals g to the y to the x. You cannot learn g to the xy without knowing x or y and these kind of things. Now, on the right-hand side is our agile version. If you provide it a strong Diffie-Hellman group, it behaves exactly like the ideal one. If you provide it a weak Diffie-Hellman group, it degenerates so that all computations return to you the same degenerate element, which you call the bad element. Think of it as a 0. In a similar way, we can model weak algorithms for all the other constructions in TLS. Now, our modeling of the weak constructions is actually overly conservative. We are really treating them as trivially broken. And of course, if you find an attack based on weak crypto, it's most likely not going to be always practical and practically exploitable. But that's not our goal. We're not trying to find practical exploits. We're trying to say if TLS 1.3 is still secure, if it is composed with older versions of the protocol, whose legacy crypto might be catastrophically broken. So after modeling the crypto, the next step is modeling the protocol itself. On the right-hand side is the full TLS 1.3 one RTT handshake and its key schedule. The details are unimportant. It basically has 12 messages in 3 flights, 16 sets of derived keys, and then it does some key exchange. So it looks kind of complicated, and if you add to it the pre-shared key-based protocol and also TLS 1.2 and other legacy versions that you might want to include in your model to check for downgrades, it looks even more complex, but actually this is exactly the kind of thing where tools like Proverif and Tamarin are designed to do. So writing a model for that one and then transcribing it in Proverif is actually very easy. It takes about 1,000 lines of code. One of your students could do it in a few days, maybe a day even. But the key effort here is on how to specify the security queries and how to do the verification. So for example, we might want to write our security goals, and our security goals would be the standard ones. Messages between honest peers should be secret, should be authentic, should not be replayable, should be forward secret, and so on. And in Proverif, the syntax of these kinds of queries roughly looks like the thing on the bottom. We are asking whether a message sent from an anonymous client, like a browser, to a server S over a connection con is secret. And we ask in Proverif, please tell me if the attacker can learn this value, which is what the query at the bottom means. So if you ask Proverif this query for TLS 1.3, the first thing it will say is, no, this is not true, because there is a possibility that the attacker may have compromised the server's key. So then you evolve, you refine the query, and you say, well, okay, so is that the only way the attacker can know the message? And Proverif says, no, there's another counterexample. The authenticated encryption algorithm that you use might be weak, and so on. So you keep refining it until you finally get the strongest secrecy query that you can prove, in the sense that Proverif cannot find any counterexample on it. And this is the strongest query in the sense that every one of the disjuncts that you see there corresponds to a well-known attack on the protocol. And it also is necessary. If you remove it, the query no longer succeeds. Proverif will find a counterexample. So one way of reading that in English is the following. Messages on TLS 1.3 connections between honest peers are kept secret as long as the following 4 conditions hold. The first 2 are as expected. The authenticated encryption algorithm should be strong, the Diffie-Hellman group used on this connection should be strong, etc. The next 2 actually show us something about downgrades. It says that the server should not use a weak hash function for signing with its private key on any connection. If on some other TLS 1.2 connection, the server used its public key or used its private key to sign using a MD5, for example, that signature could be then used to break your TLS 1.3 security. Similarly, if the server participates in an RSA key exchange is using the same certificate as it's using for TLS 1.3, then a Blankenbacher attack on the TLS 1.2 key exchange could then be used to forge signatures for TLS 1.3. And this is a well-known attack also published 1 year ago, I think in Ezorix. So these are all known problems of the spec, but our analysis confirms that these are the only conditions that you need for downgrade resilience for TLS 1.3. In particular, it identifies the weak algorithms in TLS 1.2, RSA key exchange, weak hash functions, that you must disable if you want to safely compose it with TLS 1.3. So that was the symbolic analysis. So the second part is about building up to a mechanized cryptographic proof. So this part we do it in Cryptoverif. So what we did was we took the same protocol that we talked about, the long protocol in the symbolic model, and we broke it up into several components, and we modeled it in Cryptoverif. So one component was the handshake protocol that uses pre-shared keys. One was the handshake protocol that doesn't use pre-shared keys. And the third is the record layer protocol, which also combines with it the key update protocol and the 0 RTT, 1 RTT, 0.5 RTT data exchange. So we note that in the Cryptoverif model, because for the reasons I'll show you a little bit later, we do not model all the other features that I talked about in the symbolic model. We don't model legacy crypto, we don't model negotiation, and we also don't model other features of the protocol like post-handshake authentication and so on. But even so, the full model, the Cryptoverif model, is actually quite large. It's 5,000 lines of code, including about 2,500 lines of cryptographic assumptions. And this already gives you an idea of where the effort in the cryptographic proof is going to be. It's going to be on precisely specifying the assumptions and doing the proofs. So Cryptoverif proofs are not push buttons. So in Proverif, you give the model and you ask the query, and Proverif will give you a counterexample. It was like really a push button tool. In Cryptoverif, the proofs are semi-automated. They require user guidance. The proofs themselves are a sequence of game transformation, and the user tells you, sometimes has to guide the prover into doing the right transformations. Each step relies on some very precise cryptographic assumption on some primitive used by the protocol. The overall verification strategy that you use in Cryptoverif is actually quite similar to the kind of paper crypto proofs for TLS 1.3 that have already been published, but there are some quirks of the tool and sometimes some limitations of the tool that may force you to use a slightly stronger assumption or a slightly different proof strategy. So let's just look at the assumptions, right? So to prove TLS 1.3 draft 18 secure, we make a number of assumptions on the core crypto primitives. Some of them are bog standard. So the Diffie-Hellman group must satisfy gap Diffie-Hellman. The signatures must be unforgeable, hash functions must be collision resistant, the authenticated encryption must be authenticated encryption, whatever, right? And these assumptions, even though they are kind of somewhat strong, are justified, at least in TLS 1.3, by the fact that, in fact, there is no inconsistency between these assumptions and what the standard has. The standard only mandates strong algorithms for all of these primitives. In addition to these standard primitives, there are some more unusual assumptions that we need in order for our proof. And some of these assumptions are sort of intriguing, let's say. So the first one is that the shared secret computed by the elliptic curve Diffie-Hellman cannot be a sequence of zeros. And this is because if it were a sequence of zeros, in our proof at least, there is an ambiguity between PSK-only handshakes and PSK-ECDHE handshakes. In general, you may want to avoid this case anyway because it probably indicates that you're in a small subgroup, but that's an independent concern. We also require that the shared secrets don't have that form there, that sort of ugly-looking form in the middle of the slide. And that's because if it has exactly that form, then we have collisions between different stages of the key schedule, where certain keys which are generated at stage A could be confused for the keys that are generated at stage B. This is a fairly technical concern, probably does not reflect a real attack, but this ambiguity kind of causes our proofs to not succeed. So we actually need to say that this cannot happen in order for our proofs to succeed. Interestingly, this particular ambiguity was independently discovered and discussed on the TLS mailing list, and since then there's a change in draft 18 which exactly addresses this, and so this assumption is no longer needed. This kind of shows you how the analysis may sometimes uncover some assumptions which actually have an impact on the way the standard should be designed. Finally, we need a bunch of assumptions for HMAC in particular, and somewhat unusual assumptions to account for all the different ways that it's used in the protocol. So once we have done this, right, once we have done all this proofs, we need to kind of, for the different stages, we need to put them together. So we have a proof for the TLS protocol with pre-shared keys, a proof for the TLS protocol without pre-shared keys, another one for the record layer. We want to show that the keys generated without pre-shared keys can now be used as a pre-shared key for the next handshake, so it can be used for resumption. We want to show that the keys generated by both can be used by the record layer safely, and the keys of the record layer themselves can be used for key update. And this whole proof, these compositions are done by hand. They are not done by cryptoverif. It's kind of involved, but at the end of it, you get a proof for the whole protocol. So we've done symbolic analysis. We have done a crypto proof. Now, how do we link this to a reference implementation so that we know that we're not missing details? So we built our own reference implementation of TLS called Ref TLS. It supports TLS 1.0 to 1.3. It interops with all draft 20 implementations out there right now. And it's written in JavaScript. And that is primarily because of two reasons. A, it's very easy to deploy. B, we already had tools for analyzing JavaScript code. But as a consequence, it's also very clear that this implementation is meant for early adopters, researchers, this kind of thing. It's not for production use. Yeah? So from this implementation, we extract the core protocol functionality using a tool that I'll describe. And then we can integrate that into our proverif models, into the models that we are using. And in this way, we can keep the implementation and our models in sync. And this kind of procedure ensures that in our models, we did not forget some crucial RFC implementation detail because we are forced to keep it in sync with the implementation. But note that although we are verifying this little core protocol part, we are not verifying most of the implementation. This is nowhere near as a verified implementation in the sense of me-TLS like Cedric was describing. The architecture of the Ref TLS is as follows. On top, we have the application which is written in JavaScript. It could be like a Node app or an Electron app. In the middle is the protocol layer, which is again divided into three. It's all written in Flow, this statically typed variant of JavaScript that comes from Facebook. In the middle of it, we identify and isolate a core protocol module. And this core protocol module has the protocol state machine and all the crypto-relevant information. The keys of the protocol are all kept isolated within this module. This module, this core, is written in a language called ProScript, which was presented at EuroSNP last month. And this is the type subset, JavaScript subset, whose main feature is that you can extract code proverif models from it. So from this core protocol model, we can extract out proverif, a fragment of a proverif model, and extend it with queries and top-level processes, and then analyze it. So that allows us to keep our proverif models and the code in some sort of sync. So more details in the paper. Just a summary of results. We presented symbolic analyses, cryptographic proofs, and a reference implementation of TLS 1.3 draft 18. But our work comes with many limitations, and there's lots of ongoing work to kind of to improve on this. Our symbolic model ignores many features of the protocols, which we would like to add. Our cryptographic proofs includes many features of the protocol as well. Our reference implementation, only a very small fragment of it is verified. It has a large trusted computing base. So all of these results should be taken with a grain of salt, but I think we have shown that our proof methodology and toolchain is useful for a comprehensive analysis for a complicated protocol like TLS 1.3. So all our code and models are under active development, as you will see at the Git log at that URL, but I welcome you to download them and send us comments on any of this. And I think I'm done. Thank you.
One of the most beautiful things in the paper from 2 years ago was the side-by-side graphics with the red and the green, showing all of the paths that should not have been there or that were very surprising. I wonder whether in this case you didn't need to do that because you have in the reference implementation gotten rid of all of those paths.
So that's a good question, actually. One of the main design points for our reference implementation was to design a very simple state machine which avoids a lot of those crazinesses from the messy state of the union paper. But this is not the final answer. In messy state, we were analyzing other implementations. TLS 1.3 implementations are just being pushed out right now. And I'm totally anticipating that some student in the audience will take a look at all of them and find lots of green and red arrows on them in the next 6 to 8 months as well.
Thank you.